Sure. So, Professor. So.
Okay.
Yeah.
So today we continue to discuss the continuity properties of Gaussian random processes and fields. I recall that situation which we consider is following. We have Gaussian process with some parametric set T capital. And as I said to you last time, T capital, it is not necessary interval of the real line. It can have much more complicated structure. Psi is Gaussian. Which means that finite dimensional distribution of psi are Gaussian random vectors. So, by definition, it means that for arbitrary Tn, psi T1, psi Tn is Gaussian random vector. We know that distribution of Gaussian random vector is completely defined by the mean and covariance. About our process, during almost all lectures, we will suppose that expectation is equal to 0. Because of simple reason that this is a deterministic function, and we have a lot of tools for mathematical analysis to study deterministic function. So only one characteristic which we have for our Gaussian random process is its covariance function, K S T, which is equal to expectation of psi S psi. And we know that this function completely defined distribution of the process psi. So we must to have a condition in terms of the function k, which will lead us, for example, to the continuity of our process psi t. Last time we considered Kolmogorov condition for continuity of our Gaussian process. We considered the case when T is in Rn and T is compact. And we discussed that for psi have a continuous modification, it is enough to check that it satisfies a Hölder condition. It satisfies a Hölder condition with respect to square norm. So, if there exists such constant c and alpha greater than 0, that expectation of psi t1 minus psi t2 in square is less than c multiplied t1 minus t2 alpha power, then psi has a continuous modification. Then psi has a continuous modification. I recall to you this result in order to emphasize that despite of this form, this is purely finite dimensional statement, because behind of this statement we have the Kolmogorov condition for arbitrary stochastic processes in with the parameter set from Rn. And for arbitrary stochastic process, we have such kind of condition. Q1 minus 2 not and here is n plus alpha. So you see, for arbitrary we actually derived this condition from those one, using the property of Gaussian moments. We mentioned property of Gaussian moments, so we calculate higher moments up to the case when alpha multiplied by something became to be greater than this dimension. And we can do this because of Gaussianity. But still, we must know where to stop. So this is purely finite dimensional statement. If you have finite dimensional compact and Gaussian process, which is Hölder in square norm with respect to usual Euclid norm, it's a set of parameters, it has a continuous modification. But last time we have seen examples when this parametric set is not a compact set in finite dimension. What we have to do in this case? So today we will discuss some general approach which leads to general condition when T is not a finite dimensional compact. So let me start. So I will consider the parametric set T capital and Gaussian process psi t on this set. Now let us equip this parametric set with the natural distance related to Gaussian properties. So I will define the distance on the set D by the following rule: T1, T2, T1, T2, T1, T2 is equal to the following. It will be expectation of the side T1 minus side T2 in square, and here is 1. This is, let me say, distance in brackets. Distance. Why? To check that some function is a distance, we need several properties. Because here I wrote usual L2 distance between random values, we understand the triangle inequality holds. So triangle inequality holds. Second one, symmetry. Symmetry. It also holds. It's trivial because here we have square, and it doesn't depend on the order of this difference. Now, the third one property is the following for the distance. D as t equal to 0 must be equivalent to t equal s. Yes, but evidently one can produce example when this is not true for arbitrary functions. For example, if psi t is equal to 1 variable, for example, eta for every t, then this equality will hold for any pair x in t. So this is not a distance, a real distance, but it doesn't matter. Maybe it glue up some points of our parametric set. It's even better for us. So from this moment, I will forget about this property. If you want, you can suppose that it holds, that our process is such that, or you can just think about these two properties, because statement which I want to present to you does not depend on this property thing. Now I will suppose that t with this distance d, I still will call it distance, is a compact. Tg is a compact. Here we must stop for a moment and recall what is it, because usually when we discuss compact sets in Euclid space, everybody knows what is it. This is a bounded and closed subset. Yeah? But when we have just metric space, we need to recall what is the compact. And for our purpose, I prefer the following definition, that it is compact if for arbitrary open coverage of T, one can find the finite subcover. It means that if we have a union of open with respect to this distance sets which cover T, then one can find a finite number of these open sets from this family, which also will cover our T. This is a general definition, and if we look back, it can be clear that in the finite dimensional Euclid space, this definition clearly leads to the previous one, that the compact set in Euclid space is bounded and closed, and vice versa. So here is the definition of the general compact, and this definition leads to very interesting property of the compact, because as we mentioned, now compact set can have arbitrary structure. For example, it can be a subset of some functional space, or space of sequences, or some other very complicated space. So we need to understand how to measure complexity of the compact. How to measure, how one can say that some compact is much more complicated than other one. How to do this? And people trying to understand how to measure complexity of the compact up to the modern time. But one of the most important, most known definition of the complexity of the compact is related to the notion of Kolmogorov entropy of the compact. And it was produced by Andrei Nikolaevich Kolmogorov in the mid of previous century. And his aim was to understand some problems with informatics theory and with theory of approximation of the function. But the definition was so fruitful that it occurs that it arises in very different situations, also in the theory of Gaussian process. So let me introduce to you the notion of excellent entropy, which was proposed by Kolmogorov. Let us take some epsilon which is positive. Then, of course, our compact T can be represented as a following union of the balls. Here is Bxd. This is open ball Bx. This is open ball of radius epsilon with the center at x. It is evident that if I take all centers, all points of T as the centers, I have such an expression. theta. But see what happened. We have here open covering of our compact set. From this, we understand that since T is compact, then there exists finite subcovering. Then T is equal to union of some k equal 1 and b x k. So there exists finite number of the balls of radius epsilon which cover our T. And of course, maybe this choice of the finite family it is not unique, yeah? But one can try to find the smallest number of the balls of radius epsilon which we need to cover T. And let us denote n T epsilon will be the smallest number of the elements in such family. The smallest. Then one can consider logarithm of this number. So let us define h of T epsilon as a logarithm of n T epsilon. This is exactly Kolmogorov entropy of the compact T. This Kolmogorov entropy So in this way, one can measure complexity of the complex. To understand that this is a really characteristic of the complexity of the compact, let us consider some examples in order to understand the behavior of such function. Let's start from the one-dimensional interval 0, 1. Suppose T is 0, 1 with a usual Euclid distance. Yeah. Then, if we consider n T epsilon, then one can see that it is equivalent to 1 or 2 epsilon when epsilon tends to 0 plus. Yeah? Because open ball with a center at some point is just interval of the length 2 epsilon. How many such intervals we need to cover the interval of the length A? 1. Just this one. From this, moreover, it is not only equivalence, but with arbitrary constant 1 plus delta, 1 minus delta, we have even an inequality. So I wrote it this way. From this point of view, one can check that logarithm and the epsilon now is equivalent logarithm of 1. Yeah. I forgot about constant, yeah, because we take logarithm. This is a trivial calculation. Now let's begin to consider higher dimensions. Yeah? So I will put here n. And this is a case of the cube in the Euclid space Rn. What happens in this? Also, one can check that now whatever this number of moles of radius alpha which we need to cover our have the following growth. Yes, why it is true? Because if we produce this quadratic lattice, then we will get some constant multiplied by this, yeah? And it is evident that the volume of the ball of radius epsilon is some constant which can be calculated using gamma function multiplied by the radius in n power. So we have the estimation from below and above with the same multiplier like this one. I recall that I denote it in this way. So we have the constants, and after we take logarithm, we will get here n. This is the answer. So you see how Kolmogorov entropy reacts on the dimension. We just have here n. From this point of view, one can expect that if we consider infinite dimensional ball, for example, one can take a Hilbert space with infinite dimension, which is analogous to Euclid space, then we will have here infinity. And it's true, because maybe you remember from the student course in functional analysis, the ball in infinite dimension Banach space is not compact. Yeah. So you see such a measure of complexity of the compact. It's entropy. It's entropy. By the way, one can consider other examples of the compacts and get other growths. For example, here, let me give you a very interesting and useful exercise. Proof that in the space of continuous functions with the uniform norm, such functions such as that k, it is f from 0 is equal to 0, and f minus fs is less or equal to t minus s. So let's check that this is a compact in this space is this is one statement is compact, and another one is that its entropy H K itself is equivalent to some constant multiplied by x. Okay. Let's check. So you can see that we can produce very different rules, and from this relation one can evidently understand that this is not finite dimensional compact. Yeah, this is much more complicated object. As I said to you, we study now a parametric set of general structure. So we can consider even such compacts. Now let us think why I am speaking about the entropy of the compact relatively to Gaussian complexes. It occurs that this is a very related things. And let me explain you the idea why it's happened. Maybe you remember the idea which I explained to you last time of the Kolmogorov condition. So let me recall to you Kolmogorov condition. We just have the expectation of the psi t. This is Kolmogorov condition for general process psi s, and is less than c t minus s 1 plus beta. Yeah. How do we prove it? We just do some partitions of the interval. For example, partition of the 2, 1, 2 n. Then consider set n, which will be a maximum of the oscillation of our process in the points of the partition, maximum theta k over 2m minus psi k plus 1 over 2m k equals 0 up to 2m minus 1. And then using this one and Chebyshev, one can check that trivially the series zeta n converge. It's okay. So what we can do then we can prove that our process psi, when is restricted on the one of the two rational numbers, is uniformly continuous. After this trivial consideration leads to existence of the continuous modification. So, what was the main idea? To have increasing partition and to use condition of the theorem in order to control the oscillations in the partitions. Exactly the same we can do in the arbitrary.
Professor,
But
excuse me, Professor.
but what we will use instead of this increasing partition? And the answer we already have, because if we will have arbitrary compact T, then what we can do? We can take epsilon equal 1 2 over n, for example, and then take these points from the smallest epsilon covering, yes, and then take n plus 1, add new points, and so on. So in this way, we will get more or less the same picture as before. But since we have now not the interval, but arbitrary compact, we will have here, instead of this, we will have n t epsilon, yeah, n t 1 over 2n numbers here in this sum, more or less. Yeah? So when we will apply here Chebyshev, we will need much more efficient inequality. And it can be done because now we know that our process is Gaussian. You remember that in Gaussian case, one can forget about this. One can put here arbitrary gamma, that increase
Excuse me,
moment.
Professor.
What?
I'm sorry. We can't see the lattice index on the equality.
Oh, I see. Thank you very much.
Yeah.
So one can use Gaussianity of psi, and for Gaussian case, one can check that, for example, from this inequality, maybe even here, I will put here ds square. Then one can check that probability that sine t minus sine s is greater than some u is less or equal than, and here we will have this let me here we will have d ts maybe, let me check, and e minus dts square or 2 minus 2, yeah, in such a way, yes. And here maybe, let me check carefully, maybe minus 1, but it does not matter what we, this is the main term, because you see this minus 1. This minus 1. So one can check the convergence of those series theta and now is related to the convergence of the series from logarithm of this. So now we understand this is not a proof, this is just idea, but this idea leads to very nice theorem, which was proposed by Richard Dudley in 1967. Actually, it begins from Sudakov inequality, then the story was ended by Dudley. That if the integral from 0, for example, 1, here is epsilon entropy outcome dx conversion, then psi has a continuous unification. So we have such a theorem which relate complexity of the compact to our and you see that this theorem of course cover all cases which we mentioned before, these finite dimensional cases, because of the growth of the entropy for finite dimensional compact is most logarithm. So logarithm is 1 or 2 is integrable, and one can say that everything is okay and psi has a continuous multiplication. This is the example of the work with arbitrary Gaussian process using the structure of the space of the parametric space. Now we will go to the estimate to the behavior of the process on this space. Let me explain you what we will consider. Suppose that T is compact, and psi is continuous. Gaussian process on T. Since it is continuous, then one can define, for example, the following random variable. Zeta, it will be sup of psi t when t just it is I can write even here even maximum. Good exercise will be checked that this is a random variable. Yeah? But now it is random. So one can check that sup of psi now is random variable. And of course, one can look for the distribution. And we will discuss today the estimation of the probability that zeta is greater or equal than some level u when u tends to plus p. So what is the tail? What is the tail asymptotic of this quantity? This will be our problem. And as you remember, Our mini course of lectures is titled as a geometry of cubes, and it surprises the cubes that this asymptotic is related to geometry of trajectories of our physics. In order to understand this, let us begin with the so-called Rice formula. Rice formula. Let me write the title. Rice formula for stationary Gaussian process. I will discuss the following question. Let us have psi t equal now stationary Gaussian. Stationary Gaussian. Let me recall what is. As we agreed, its mean is equal to 0. But we have here word stationary, and it means that its covariance function KTS does not depend on the moving our parameters along the line. It depends only on the distance. So it's equal to some gamma t minus s. Here is the definition. Stationary process. And in addition, it is harsh. For us, it is important. So we have such process. Of course, one needs some examples. And you remember that most difficulty in building of examples of Gaussian processes is related to checking that some function is a covariance function, that some function is positively definite. But I must say that for this case, we don't need to work hard because we already have the big set of examples of positive definite function. This is Fourier transform of some symmetric measures. For example, it is easy to check from the theory of characteristic functions, there's such functions like gamma of t is equal to e minus t squared, e minus this one, or 1 positive, because these are characteristic function of Gaussian distribution, this is characteristic function of Cauchy distribution, and vice versa. This is the characteristic function of double exponential distribution, and so on. So one can understand that we can have a lot of such examples of gamma for free. Now, let me take, for example, let me take, for example, this function gamma t equal a minus t squared. Then one can check that for such function, not only psi is continuous, but also psi has a continuous derivative. So psi prime has a continuous modification. If the question arises, how I can check this? The answer is simple. One can guess that maybe if we have infinitely differential covariance, then the process is infinitely differential in two sets. It is trivial. Then one can get the covariance of this one process and apply again for the condition. So this for smooth covariance we have this for Gaussian case. Now since trajectories of psi are smooth functions, one can ask about their behavior. What I mean by the word of behavior when we consider just a one-dimensional smooth function. Let us draw a picture of maybe typical smooth function. Yes, everybody can do this in such a way. This is a graph of the typical smooth function. And then what will be the characterization of its geometry? One can say that maybe its geometry can be characterized, for example, in such a way. Let us take some level u, and try to understand how many upcrossings of this level we have on the fixed interval. So how fastly our function oscillates. What I mean upcrossing? Let us magnify this picture. Here is our level u, and upcrossing is the form. The graph of our function intersects this line from below to above. Yeah? So the derivative here is positive. This is upcrossing. And it is evidently that the number of upcrossings is related to oscillations of our function. For example, if we consider a function f of t equal sine omega t, this is not probability event, but this is from physics, this is just frequency. Then, of course, when omega increases, we will have this number of approaches also will increase. So, in some sense, it characterizes our function. Let me denote this number of approaches with the level u by n of u. This is by u. Is a number of approaches. U on the interval for example 0, 1. Then our purpose now is to find expectation of this quantity. What is this? What is this? Now, let us proceed as follows. I will try to find this expectation as so what we need? We need to calculate cases where psi of t is equal to u and psi prime of t is positive. So we need to calculate such events, such numbers of t. I will do this formally, but we will see in our lectures in the future that sometimes these formal calculations are very useful. So we want to calculate such events from 0 to 1. Then I need this. I will play delta function u psi t and I will put here indicator of 0 plus t from psi prime t. This is a very formal expression because it contains this new object for us, this delta function. So let me here stop for a moment and just I will try to explain what is it. What is it? Actually, let me emphasize that we don't know precisely what is it completely for the, because I recall you, we just want to have this. So what I want, what I need is the point. I just want to know what is this. Yeah. For some random variable. It's enough for me. Because I will put sign of expectations. I will not work with this quantity at all. I will work only with the expectation. So let's check what we will have. By the way, let me ask you, maybe Professor Han, we have today 2 lectures.
Yeah.
Do we need to have a break now, or I can continue and stop, for example, after 50 minutes?
Professor, maybe we have a break. Is it okay?
Mm-hmm. Okay, so what time? Let us have a break up to 10 minutes. Is it okay?
Yeah, very good. Yeah, nice.
So I will not stop the conference. Okay?
Yeah, okay.